This is a video demonstration of the final project submission made to Introduction to Operating Systems course for the fall 2025 semester. In this project, we have implemented a user level threading library. Going ahead, what does our user level threading library do is, so for the user space there are n threads, but for kernel there will always be one process. The kernel will never get to know that there are n threads being executed. For the kernel, it always remains one process. Our library acts as the orchestrator for those threads and manages the CPU context switching for those threads. Going ahead. So the key components for our demo and presentation would be the thread management, how it is done, context switching, how we switch context for CPU, schedulers, the round robin approach that we take, synchronization primitives that we use, and how memory is managed. Going into each, first coming to the thread structure, we have a thread ID to identify each thread uniquely, and we have a return value. The stack and SP are, this is the base stack pointer and this is the SP. So thread state is the current state where thread is. It starts with unused and it ends up at unused. Unused means that this thread and the memory allocated to this thread is empty, anyone else can take it. Going ahead, memory allocated. So for every thread we allocated a fixed size of 4 KB, that is 4096 bytes. And since there are maximum of 16 threads, that scales up to 64 KB. For XV6 OS, assuming 64 KB as the memory available is a rational assumption. This is the stack structure. We have, it starts with the initial stack pointer and it ends at bottom of stack. It will always grow downwards. It will have local variables, and the last thing before bottom of stack is the return address. Going ahead, so for the indexing, there are 16 threads. The index is done from 0 to 15. 0 is the current thread that is being executed. 1 to 15 are the thread identifiers. Any thread that is initialized will get a number somewhere in between 1 to 15. 0 is not allotted initially. Going ahead, state definitions, as in the thread state that we had defined in thread structure. There are 5 states: unused, runnable, running, sleeping, and zombie. Discussing how each of them is managed. So any thread starts with unused state. From unused state, they could go to runnable, running, or sleeping. Runnable is that they have access to all the resources that they want and they are waiting for free time of CPU. Once CPU is free, they will transition into running state. From running, they can go to sleeping because they want a lock, because that particular thread wants a lock, but the lock is currently acquired by someone else. The thread yields the CPU and goes into a sleeping state, waiting for a wake-up call from the CPU. Once it gets a wake-up call, it will again become runnable and it will go running. Once running is done, it does what it wants to do. Then it returns the value and it goes into zombie state. Zombie state is that the memory is still there and it is waiting for someone else to clear the memory. Once the memory is cleared, we again get back to unused state. That means the 4 KB stack is empty and anyone else can come and occupy it. That is the state management. Implementation details. Coming to implementation details, first we go with the scheduler algorithm. We have used round robin scheduling algorithm. We had previously used it in assignment 2 and assignment 3. So my bad. Yeah, this is the code for scheduling algorithm. Okay, why we used it is because we don't want CPU monopolization by one heavy thread and we don't want to starve any thread for a long period of time. So that's why round robin, because it's a fair approach to allocating CPU time. Going ahead, context switching mechanism. So this comes out to when we want to switch from one thread to another, we need to switch the CPU. We need to switch the CPU state. So this can't be done directly via C. We need a kernel call. So here we are writing the explicit instructions in assembly implementation. One can go over the uthread switch.s file inside source folder to see how this has been done. I have added proper comments for users to understand. how this is getting executed. Alright, moving ahead. Registers is the place where we store the pointers to stack CPU, source index and destination index. Right, okay. Going ahead, how sleep wake up implemented. So for any thread that wants to get a log which is currently required by someone else, it goes from running to sleep state and it waits for a wake up call. When it goes to sleep state, it will call thread schedule, that is it eats the CPU to anyone else who wants to use it. That is it. This wait count will cover under the next part, how wait count and wait queue are addressed. Okay, going ahead. Wake up operation is whenever the log thread was waiting for is available to be acquired, the thread gets a wake up call based on whether it was at the top of the queue or not, wait queue or not. This is the part. Again, from sleeping state it will transition to runnable state. That is it. Wait queue management. It is a queue and we have implemented it using array data structure. We haven't used a linked list because we didn't want a dynamic memory allocation. In essence, in asymptotic complexity, dynamic allocation would have looked a better approach, but since O of n is 16 and 16 is a very low number, and I feel the constant time of dynamic allocation would have far crossed the time it takes to use an array. That is it. Synchronization primitive. This is for the part that how do we address the wait queue. So we have a mutex implementation, we have a semaphore implementation, we have a conditional variable implementation, and we have a channel implementation. Right, these are the 4 parts. Mutex comes directly from the assignment 2 and assignment 3 that we did. That's where we understood how to implement mutexes. The other 3 parts have been done in this. That is it. Going to the, this is the design choices section, but I feel I have already addressed this part while explaining the above part. I'll directly jump to the demonstration part. So for demonstration, we have 5 test cases, 6 test cases that show how each of the part is executed. Going to the first simple test part. The simple test part just is there to show you that the threads are being executed parallelly. The print order of thread assures user that they are not executed in series. As you can see, before one is completely done, it yields up and lets other thread execute. But at the end, each thread finishes the job that it had to do. That is it. And this is the shared counter test. This is for the mutex part to show the results. What happens when we have mutex and we don't have mutex. When we have mutex, each thread here is incrementing the variable by 1000. So, one at a time and 1000 iterations to increment it by 1000. So, yeah. If we have a mutex, the variable is incremented to 3000 at the end because 3 threads, 3 into 1000, 3000. But if we don't have a mutex, we create race conditions and the variable ends up never reaching 3000. So in this particular case, it ended up at 1000. Going to the producer consumer semaphore, this shows the synchronization primitives implementation. This is using semaphore. We have done the same using channel 2. We will cover that in next test case. So here we have a buffer size of 5. We have 3 producers, 2 consumers. Producers keep on producing till the buffer size reaches to its max capacity, and then they hold on for buffer size to again become less so that they can publish more. In the meanwhile, since we have a round robin implementation, consumers also take up CPU time and keep on consuming. So as you can see, the print order of it is interleaved, showing that threads are being parallelly executed. And once the buffer reaches 5, the publishers have to wait for consumers to finish consuming. That is it. This was using the semaphore implementation. We have done the same using channel implementation too. So this is the part where we have channel implementation. In both parts, each of the producer publishes 10 messages. So there are 3 publishers, so total 30 messages, and we have 2 consumers. They end up consuming all the 30 messages. You can go through the print logs to see that every and ensure that every message is being consumed. Okay. The print logs will look essentially same because the same part is being done, only the implementation details have changed from semaphore to channels. Okay, that is it. Coming to the reader writer log. This part is done to show that how multiple readers can read at same time, but when a writer writes, no reader gets to read the wrong value. All reads are blocked until the writes are finished. So here, as soon as writer 1 starts, reader 1 to 3 are blocked, no one can come in between till both the writers are finished. Once the writes are finished, and no reader gets to read the wrong value, that is no one reads 10, everyone reads 20. And this part has been repeated multiple times to show that this wasn't just luck. It happens each and every time you test it. That is it. Coming to the last part, that is file producer consumer. Yeah. Yeah. So this is the file producer consumer. Here you can see every time this has been currently done via blocking. So whenever a producer tries to write, all the consumers are blocked. Consumers are readers and producer is a writer. So whenever a producer writes, all the reading threads are blocked. Not just the reading threads, but all threads are blocked. That is it. Thank you for watching.